Welcome to this channel. I'm Chris, and today we want to talk about the basics of Banach spaces. Why do we do that? It's a very important algebraic construction for functional analysis because analysis on or functional analysis on not Banach spaces is really strange, and one has to think if this is really analysis anymore. But this is another philosophical question we don't want to answer here and discuss. So first of all, we have to define what we mean by that. A Banach space is a norm space which is complete. Yeah. So every Cauchy sequence converges in that space. Yeah, this is important. You will see in a few moments why I told you that. So before we do that, a few examples. First one you might know. Let's pick a measure space and a p between 1 and infinity. Then we define LP space by the quotient space of the actual LP space and the null space. Why do we need that? If we don't do that, so looking at that wouldn't be a Banach space because it isn't even a normed space, a fully normed space, because the norm, the LP norm on this space is a semi-norm. So we have a problem with the positive definiteness. And this is because of dealing with measures. So we have this property, so a function being zero just almost everywhere because of integrals and measures. Okay, and this is an example of a general technique we see often in functional analysis. So if we have a space with just a semi-norm, we can get a normed space by yeah, let's say overlapping infinite of the semi-norms. What do I mean by that? You build the quotient space with the null space, okay? This is a basic concept. We will see a few times in this series. Okay, and the proof of that, I think I will do that in the series of measure theory or the integration theory. So yeah, I think 2 times is a bit too much. So one video for that is enough. Short reminder, be careful. Of course, we have here a quotient space. So yeah, if we're exact, then the elements of that are not functions. So writing f an element of AP is, yeah, it's wrong, but in general, we picked a representative of its equivalent class, yeah? And then we can say, yeah, this one is an element of AP, okay? But everyone does that, so we will do that too. So from A, we get directly that a Sobolev space with its norm is also Banach. Yeah, of course, the Sobolev space has many LP properties and the groundbreaking basic one. So by the completeness of LP, we get that this is a complete space too. So now from analysis 1 and 2, or maybe more analysis too. We know that all norms in Rn are equivalent. And now be careful, this is not true in general. So in infinite dimensions, this is false in general. And even more, it's really, really crucial which norm you choose for an infinite dimensional space. And let's look at an example. So let X be a topological space. And then we look at this function space CB of X. And this is the space of all bounded and continuous functions. Okay? Yes, this is, whoops. This is the space of all bounded functions. So dealing with function spaces is really important and yeah, classical. Okay, and now I assert that this is a Banach space. So if we take this space with the supremum norm, then it's a Banach space. But if you change the norm to the, for example, to the L1 norm, it is not a Banach space. Okay, so first the counterexample to this. Let's consider this sequence of functions. We define it like that. So this is probably the most easy one you can define as a counterexample. So we see that this is in ZBX. Yeah, it's bounded because this is compact and we don't leave the compact interval. And it is continuous. You can see that if you look at the bounds. Yeah, so this is continuous. And also it is a Cauchy sequence. Yeah, I didn't show that here, but it isn't really that hard. Yeah, it's an epsilon argument about 2 to 3 lines. And the limit of it is this function. And this function is not in CBX. It's even not in CX because it's not continuous. Yeah, just a short reminder. This space and this space are the same if we have a compact X, yeah? Because then we have a continuous function on a compact set, so it attains its maximum and minimum, so it's bounded. So then they are the same. Okay, just a short reminder. And for the first one, the proof, I give you the idea because the details are not really hard. If you have this right idea, the idea is that we have a setting in which we have uniform convergence. Yeah, so we have convergence in the norm, and this is the supremum norm. So we have uniform convergence, and yeah, the limit function of a continuous uniform continuous sequence of functions is continuous too. Yeah, and this is also a short epsilon argument. And for the guys above you who are interested in algebra, in general, if we deal with function spaces, what we have to do to show that it is Banach, we have to pick a norm which ensures that we also have the property of the function space afterwards, after the convergence. Okay, so this idea is a very good one in general for function spaces. So you pick a norm in which you have a statement like that for the property of the function space you deal with, of course. Okay. Lastly, a short remark. We know that R is complete, yeah? And we can generalize that. So if we have a complete field, K, and the dimension of the vector space, the norm linear vector space with it, if it has a finite dimension, then it's complete. And how do you prove that? You prove that with norm equivalence and using the basis of elements. So basically, this is a very similar proof to that R is complete. Yeah, if you have that in mind, how we proved that with yeah, projecting into the sphere and then getting the bounds we need. So basically, we're doing here very similar one, but we're not projecting to the to the sphere. That doesn't work in general. We need then a construction, a more generalized construction, of course, but the rest of it is very similar. Okay, but you can generalize what we had today. You can transfer norm equivalence in general, but you have to restrict to something. You need that X is Banach with respect to two norms, yeah? And then they are equivalent on X. This is true, okay? And the proof of it we will see later on, later because we need the theorem about open mapping, and this is too early to tell you about that. We will see that later, okay? So that's for today, and yeah, hopefully we see each other in another video. Bye.